The two most common ingredients used in the production of media for container growing of woody plants have been sand and sphagnum peat moss. However, soil is used to a limited degree in some mixes, and various wood waste products are increasingly being used to replace sphagnum peat moss. Good container media management is basic to the production of quality container grown plants. I'm Dr. DeBusk, and this video discusses commonly used ingredients and mixes, the need for nutritional supplements and testing, and the need for media pasteurization. Sand consists of weathered mineral particles between 0.05 and 2.0 millimeters in diameter. For container soil mixes, the sand must be free of clay and silt, and the size of sand particles should range between 0.05 and 1.0 millimeters, with less than 10% of the sand in the coarse size classification between 0.5 and 1.5 millimeters. The mineral composition of the sand is related to the rocks from which it was formed. But for horticultural purposes, sand contains few, if any, nutrient elements and has no significant pH buffering or cation exchange capacity. Sand may or may not be sterile, depending on its source. The pH of sand varies with source, and most sands have a high pH and may require the addition of an acidifying agent. Peat moss is composed principally of partially decomposed sphagnum, hypnum, and other mosses. Sphagnum peat moss is the least decomposed of the three types of peat. It is light tan to dark brown in color, lightweight, high in moisture holding capacity, and high in acidity. Sphagnum peat moss will hold 10 times its dry weight in moisture, and because of its high acidity, it has little microbial activity and it is slow to decompose. Sphagnum peat moss should not be confused with sphagnum moss, which has not begun to decompose. Sphagnum moss is used by growers for packing and shipping tender plants as well as a propagation medium. Wood products of various types, including sawdust, wood chips, shredded bark, and wood shavings, are an excellent source of organic material for soil mixtures in the production of container-grown plants. There is a toxic effect, stunting and chlorosis of the plant, that can occur with the use of sawdust and to a lesser degree other wood waste products, which is related to the carbon-nitrogen ratio of the sawdust and its effect upon the soil-plant nitrogen relationship. This problem can be avoided by the addition of nitrogen to the sawdust soil mixture. Sawdust, because of its smaller size particles, will decompose more rapidly than coarse wood chips. Microorganisms carry out the decomposition and need a source of carbon found in the wood and a source of nitrogen, which will be taken from the surrounding media, since not enough is in the sawdust. If the nitrogen content of the mixture on a weight basis is about 1.2 to 1.5%, and the optimum conditions for biological activity are present, decomposition will proceed without depleting the supply of available nitrogen to the growing crop. Because sawdust contains about 0.2% nitrogen, the addition of 25 to 30 pounds of nitrogen per ton of sawdust is required. H sawdust makes an excellent water-holding ingredient for container production of nursery stock. It is lightweight and has good aeration porosity. It does not require the addition of large quantities of nitrogen to support microbial development, and it is relatively sterile. Hardwood bark, maple, cherry, oak, cottonwood, etc., is a lightweight wood waste product, which when supplemented with nitrogen makes an excellent organic ingredient for the production of container-grown plants. It may be used alone or in combination with sand. It is lightweight, easy to handle, and the CEC exceeds that of sphagnum peat moss. Bark contains all the trace nutrient elements and significant amounts of the major nutrient elements. Some fresh hardwood barks may contain phytotoxic substances that are harmful to plant growth. Composting the bark for a period of at least 30 days will eliminate these compounds. Hardwood bark is readily available in many parts of the country and is relatively inexpensive. Pine and Douglas fir bark are an excellent medium for the production of plants that require an acid root environment, such as rhododendrons. Growers have found that if the medium has no clay component, the low pH of pine bark need not be adjusted. Softwood bark, pine, fir, redwood, etc., has a low bulk density and fairly good CEC. It is somewhat difficult to wet. Use of a wetting agent is suggested, but upon wetting, it possesses a good water holding capacity together with good aeration. Some bark, such as Douglas fir, contains sharp slivers. The use of leather gloves when handling the material is recommended. Perlite is a lightweight granular material obtained by heat treating crushed lava. It weighs less than 8 pounds per cubic foot. It is sterile, has a pH close to neutral, and a water holding capacity on the surface of the particles equal to 3 to 4 times its weight. The material is without either buffering or cation exchange capacity. Perlite is a good propagation medium or as an amendment to decrease weight and improve aeration of container mixes. Vermiculite is a very lightweight, expanded plate-like material obtained by heat treating mica. It weighs about the same as perlite, 6 to 10 pounds per cubic feet, depending upon the grade. Has good water holding capacity, equal to 3 to 4 times its weight, and a good CEC. Because the material is produced by heat treatment, it is sterile. Vermiculite makes an excellent propagation medium and a media amendment for producing small container-grown plants. It must be handled with care when wet to avoid compressing the particles or breathing in the particles. Compressed vermiculite is an undesirable media amendment since it has poor drainage and poor aeration porosity. Cocoa coir is a byproduct of coconut fiber. Everything in between the shell and the outer coating of the coconut seed is considered cocoa coir. It is produced primarily in Sri Lanka, the Philippines, Indonesia, Mexico, and parts of the Caribbean and South America. The benefits are that it retains moisture, absorbing up to 10 times its weight in water. It doesn't need a wetting agent like peat moss, has greater oxygen levels, and decomposes slowly. It may have some insect repellent properties. It has a good CEC, but one that is lower than sphagnum peat moss. If it is not processed properly, it can have a high salt content. It is shipped in dry compressed bricks, so it needs rehydration and can be clumpy. A good container medium must possess the criteria and perform the various functions discussed previously. In addition, it should be readily available in adequate uniform quantities, relatively inexpensive, light enough to be handled conveniently within the nursery and to be transported economically to market, free of pests, including weed seeds, disease organisms, harmful insects, nematodes, herbicide residues, etc., or be capable of being sterilized without the production of toxic substances, for example, soluble salts, ammonia, biuret, and other phytotoxins, economically blendable into a uniform, relatively stable medium, and capable of being stored for short periods of time without significant changes in the physical and chemical properties. The UC system for producing healthy container-grown plants was developed at the University of California, Los Angeles in the 1940s and early 1950s. The primary objective of the system was to reduce the cost of production by increasing potting media uniformity, by reducing plant losses, and by lowering labor costs through mechanization. The two most commonly used mixes are 75% fine sand plus 25% peat moss and 50% fine sand plus 50% peat moss. The UC mixes are fortified with various fertilizers to provide an available supply of the major nutrients, nitrogen, phosphorus, potassium, calcium, and magnesium. The sphagnum peat moss and fine sand contain a sufficient supply of the microelements to meet the needs of most container-grown plants. However, some acid-requiring plants, for example rhododendron and blueberry, and plants grown in containers for long periods of time may require a supplemental application of iron chelate or a minor element fertilizer that contains a mixture of the microelements. The Cornell Peat-Lite mixes were developed at Cornell University in the 1960s primarily for seed propagation and production of spring annuals and bedding plants. The basic ingredients of the Peat-Lite mix are sphagnum peat moss and either vermiculite or perlite, to which are added specific quantities of dolomitic limestone, superphosphate, and a complete fertilizer with a ratio of 1:1. The Peat-Lite mixes have several advantages for growers of young plants. They are lightweight and the ingredients are uniform, readily available, and free of harmful organisms. But they have limited use in outdoor nursery production of larger plants since the medium provides no ballast to support the relatively heavy crowns of woody plants. They are used most successfully for starting seedlings and in the potting of roses and small shrubs for short periods of time. That is, potting roses in late winter and growing for 1 to 2 months for spring sale. Compost has also been used as the organic ingredient in soil mixes for the production of container-grown plants. Compost must be cured to the point in which microbial activity has been reduced and little, if any, heating occurs in the compost stack. A mixture of soil, perlite, municipal compost on a 1:1:1 volume basis has produced quality plants when fertilized with a constant or biweekly soil fertilization. The EPA regulates how municipal compost or biosolids compost is produced to ensure that it is free of harmful diseases and limits how it is used based on its heavy metal content. When it is used in potting medium, it should contain a minimum of all heavy metals, be suitable for good production, and be free of weed seed. Most media manufactured for the production of container-grown plants will require some form of chemical supplement to adjust the pH and to augment the available nutrients during the growing season. Sphagnum peat moss and softwood bark tend to be acidic and may require the addition of limestone to raise the pH if it is below 5.0. Finely ground pulverized limestone has been found to be the most effective material to increase the pH of container media, either by incorporation or by surface application. The addition of limestone is usually not needed if the irrigation water has an alkalinity or hardness above 100 ppm. Some sources of peat and hardwood bark are alkaline, and sulfur or iron sulfate should be added to lower the pH. Some of the ingredients used for producing artificial soil mixes are low in available phosphorus, calcium, magnesium, iron, and various microelements. Therefore, it is necessary to supplement the medium with these nutrients either during composting or just prior to planting. Peat is naturally low in microelements. Use only powdered or fine crystalline materials and mix it in gradually as the mix is blended. Plants growing in most potting mixes will require supplemental nitrogen and potassium shortly after planting. This can be efficiently accomplished by the surface application of one of the slow or controlled release fertilizers shortly after planting. The rates of application are frequently suggested on the fertilizer bag, but they will vary with the mix and the fertility program of the nursery. If a 1:1 sand-peat medium is used, a rate of application that supplies nitrogen at 300 ppm is satisfactory to supply the nutrient requirements of the plants for about 4 months. The goal of a fertilizer program should be to apply only those nutrients required and only in amounts that are required to produce the desired growth, flowering, and plant quality. Any application of fertilizer beyond that necessary for optimal growth is a waste of resources and can result in serious groundwater and surface water contamination. To ensure optimal growth, the media should be tested periodically to ensure the optimum levels of nutrition are being maintained during the growing season. Growing medium testing procedures vary considerably among laboratories. Data from a soil test carried out by a laboratory using one method cannot be compared to a report from a laboratory using a different method. The saturated media extract is a water extract of the entire media sample. A representative sample of the media is wetted with deionized water until water just barely stands on the surface. The mixture is allowed to stand for 90 minutes and then filtered upon suction. The filtrate is analyzed for important plant nutrients. In the 1:2 dilution method, an air-dried sample of soil and water are mixed together in the volume ratio of 1 part soil to 2 parts water. The liquid extract is then separated from the solids using laboratory-grade filter paper or common coffee filter. The extract is then ready for analysis. A third method, the Virginia Tech extraction method or pour-through method, has been developed specifically for testing media used in container production. This test allows growers to quickly carry out their own soluble salts and pH determinations. In addition to collecting a soil sample to test, growers can collect leachate from container-grown plants using the pour-through method. One of the major advantages to leachate pour-through is that there is no media sampling or preparation. Unlike soil media extraction and 1:2 methods, plants do not have to be sacrificed or disturbed for testing because the extract is the leachate collected from the container during routine irrigation. The leachate can be analyzed on-site using the pH and EC pins, or it can be sent to a commercial laboratory for a complete nutrient analysis. Leachate pour-through is best used for continuous monitoring and graphical tracking of pH and soluble salts. To make this method work best, an irrigation and leachate protocol must be established and carefully followed when sampling takes place. The key components of the pour-through method is to irrigate your crop 1 hour before testing to make sure the substrate is saturated. Place the saucer under the container. Pour enough distilled water on the surface of the substrate to get 1.5 ounces of leachate. Collect the leachate for pH and EC. Calibrate your pH and EC meters prior to testing and measure the pH and EC of your samples. If used correctly, the 3 methods of soil testing outlined here give valuable and useful results for greenhouse crops. Soluble salts are the total dissolved salts in the root substrate, medium, and are measured by electrical conductivity, EC. Measuring EC or soluble salts provides a general indication of nutrient deficiency or excess. If a high EC reading generally results from too much fertilizer in relation to the plant needs, but inadequate watering and leaching or poor drainage are other causes. Soluble salts above the normal range for prolonged periods may cause root injury, leaf chlorosis, marginal burn, and sometimes wilting. Soluble salts below the normal range may indicate the need for increased fertilization. Most greenhouse crops can grow satisfactorily over a fairly wide pH range. What action to take on pH depends on the specific requirements of the plants being grown and knowledge of the factors which interact to affect the pH of the media: limestone, rate, type, neutralizing power and particle size, irrigation, water pH and alkalinity, acid and basic nature of fertilizer, and the effects of mixed components are major influences on pH. Optimum pH values have been established for soilless media and media with 20% or more field soil. Optimum pH values are shown in the table. Another important factor in the successful production of container-grown plants is that the medium be free of organisms harmful to plant growth. Newly mined sand is relatively free of harmful organisms and can be used without pasteurization. However, most soils and some sand and peat moss have become contaminated and will contain harmful organisms such as bacteria, fungi, insects, and weed seeds. Although the growers use the term sterilization in reference to heat treatment of soil to rid it of harmful organisms, a more precise term is pasteurization, since the temperature used, 140 degrees Fahrenheit, destroy only the harmful organisms. Various means of heat treatment can be employed, but it is desirable to obtain a soil temperature of 140 to 150 degrees Fahrenheit and to maintain that temperature for at least 10 minutes, but no more than 30 minutes to destroy most plant pathogenic fungi and bacteria. Chemicals can also be used to rid soil of harmful organisms. In general, fumigants are less destructive of the physical properties of the soil than are heat treatments, but they are more costly. Following treatment, the media should be aerated for a period of 2 days to 2 weeks to allow the chemical to dissipate prior to planting. A number of fumigants available to growers will effectively sterilize media, including formaldehyde, vapam, and chloropicrin. In this video, hopefully you learned about the different types of media, common container mixes, supplements, testing, and pasteurization.